Okay, here we are. This is actually the only video that I'm making for your homework 16. This is page 241-34. I look back to your assignment. Yeah, you've got problems 33 and 40, both of which are in the same set here as 34, finding complex roots of polynomials. And this is this overall procedure takes so much time that I thought just this one time, rather than you watching me go through it, I'll just show you the result here and just walk you through it one time so you don't have to see me finding roots and doing synthetic division and whatnot. So here's the problem. A third order polynomial, find its complex roots. The very first thing we do is ask ourselves how many complex roots there are, and their answer is third degree means there are 3 complex roots. So that's a different answer than you were giving when we were finding real roots, because a third degree polynomial has as many as 3 real roots, but it's got dead on 3 complex roots. So the next step is Descartes' rule. If we look at this polynomial, everything's plus, so there are 0 sign changes for f of x, which means there are 0 positive real roots. If this thing has real roots, and it could have 1 or it could have 3, I'll talk about that more in just a moment, they're all going to be negative. And sure enough, when you insert negative x in for x here, and count the sign changes associated with that polynomial, there are 3, meaning there are 3 or 1 real roots. So you knew that from another perspective. You knew that there were 3 roots, complex roots. You knew that there were no positive real roots. So at that point, that means that either there's 1 real root and 2 complex conjugate pairs. Because of the conjugate pair theorem, complex roots occur as conjugate pairs. So either you've got 1 negative real root, 2 complex conjugates, or you've got 3 negative real roots. So as we kind of go down the list here and look at the rational root theorem, we see that this coefficient is 1, meaning that the rational roots are going to, the candidates for the rational roots are going to be the factors of 85, which I believe are -1, -3, -5, -13, 13 times, well, it's not -13, it's -17. Told you didn't want to watch me do this. It's minus, why do I have 15 here? Is 15 right? Yeah, 15 must be a real root or a factor. And -17 and -85. So that's what we've got to choose from. I then am at the point now in solving this that I've got to find a root. I tried -1, I got 40. I tried -3, I got 4. We're getting close. I tried -5, and -5 turned out to be a root. So hurrah, if -5 is a root, x minus -5, aka x plus 5, is a factor. If I factor that root out and reduce this third order polynomial through synthetic division, I find that I can write f of x as x plus 5, the factor associated with the -5 root, one of these 1 or 3 minus real roots that we're looking for. And this quadratic, I'm not going to mess around with this quadratic. I'm just going to use the quadratic formula, and I'm going to find there are indeed 2 additional roots. They're complex roots, meaning that the answer to this problem is f of x is equal to -5. F of x has roots that are either -5, -4 plus I, or -4 minus I. And if I've got space right here, that means that you could write f of x as x plus 5 times x plus 4 minus I times x plus 4 plus I. Okay. And there you have it.